Okay, I'm going to continue the volumes 7-2. Hopefully this is our real, truly last teaching segment. Unless I do have to put together something for the AP class. It's a little nebulous about what we're going to do for the AP part of the classes, but I would like all of you to finish up the actual, course, which finishes right here with volumes. So washer method continued. Let's look at a weird example. What if I ask you to find the volume of the solid generated by revolving the region bounded by the graphs of y equals secant of x, y equals 0, and x between 0 and pi over 3. In other words, you could say x equals 0 and x equals pi over 3. Either way, it will be that area revolved about, let's just say about the line y equals 4. Okay. Secant of x, if you remember, y equals 4 is up there, so I gotta leave some space down here. Secant of x starts off, well, the cosine is the reciprocal of secant, right? So cosine of 0 is 1, and 1 over 1 is still 1, right? What happens is at pi over 2 and negative pi over 2, where the cosine is 0, we get those vertical asymptotes, right? But it doesn't matter, and normally, the graph just is the parabola type things. But we're only going from 0 to pi over 3 in here somewhere, right? And y equals 0 is the x-axis, and this 0 tells us we're only starting there. So this is our little area that we're taking and revolving about the line y equals 4. And so it's looking like, probably something like this. 3, 2, 1 is where it is, right? And then it goes down. So it's probably the little reflected graph is something like that, right? Where we clearly have big open spot in the middle, space in the middle. So it's clearly a washer. And we need a big R, a little r, and an H. And since it is a vertical rotation, right, our height is a dx. Anytime that rotation is around a horizontal line, it will be a dx, okay? I'm sorry, my drawing is pitiful. But I hope you can see that when we slice it right there, it's a vertical slice, and it will have a little height of dx. Now the big R, something that causes kids to really have issues is they'll try to take the radius up to that reflected image. Always go to the original graphs that you had. So the big radius goes from that axis of rotation down to the farthest, and if I look all the way across that figure, that's just a solid 4, a never changing 4, right? Because this line, now if this was like a region that was bounded by another graph, then you would say the big R would have been, 4 minus the y value from, but it's really 4 minus 0, right? So there's our big R, a solid 4. But the little r is a changing value depending on where our little cross section is, where our little slice is. And so from here to here, remember that point xy, that length is the y value, right? But we need to get from 4 backwards down to the y value. So I'm going to say 4 minus the y value, which by the way is just the secant of x. We know we want it in terms of x's, right? So pi integral big R squared minus little r squared dx. And the integral 0 to pi over 3 was given, right? So, it's looking a little bit far away. Now, 4 squared is 16. 4 minus secant of x quantity squared is going to be 4 squared is 16. 4 double is 8 secant of x plus secant squared. Distribute that negative plus 8 secant of x minus secant squared. How nice is that? The 16s are gone. And so we're really just looking integral 0 to pi over 3 of 8 secant of x minus secant squared of x dx. Alright, now we got some, I don't remember if we actually did the integral of secant. This might be something we do in BC, but integral of secant is just absolute value of secant x plus tangent of x. Oh, it's the ln of that. Sorry. ln, absolute value of secant with the 8 there. Minus integral of secant squared is regular tangent of x, right? 0 to pi over 3. Pi times 8 ln. Of course, if you want to free response it, be kind of a wimp, you can write it in. And of course, I guess since this year everything is free response, there's no multiple choice. You could just be really careful. Minus 8 ln secant of 0 plus tangent of 0 minus tangent of 0. But tangent of 0 is 0. Secant of 0 is 1, but the natural log of 1 is just 0. So we're talking about subtracting 0 from all that. The secant of pi over 3, root 3, 2, secant is 2, and the tangent is root 3. So pi times, I guess we could say, well, 8 ln 2 plus root 3. Tangent was just root 3 over 1. I got nothing to make this easier because I don't know what the natural log of all that is. So I'm telling you, free response. Let's practice that, because if we're dealing with a free response, as long as it's not a calculator problem. If it's a calculator problem, they definitely expect you to plug it in. But non-calculator, don't even worry about it. Alright, so one more where we're going to rotate about another just randomly weird line. How about xy equals 5, y equals 2, x equals 5, about x equals 5. Ooh, I'm feeling not a washer, but a disk, because that's the same as the boundary. Alright, x times y equals 5. That's y equals 5 over x. So that's going to have that vertical asymptote. Y equals 2. X equals 5. Gotta give myself a little more room to the right. 5 over 1. 1, 2, 3, 4, 5 is 5. 5 over 2 is 2.5. So we got this thing, this curvy thing going down here, getting closer and closer to 0. Oh, 5 over 5 is 1, right? 1, 2, 3, 4. So here at 5, the value is 1. So I was trying to make it get there quicker. X equals 5 is the boundary. Y equals 2. Oh. So we're not talking about any of this bottom space. If we're talking the boundary that's bounded by the curve, y equals 2 and x equals 5, we're talking about this little bitty space right in there. And if we rotate that little space about the line x equals 5, it just becomes this little filled in discish kind of thing, right? Almost like a frisbee or something, only it's not hollowed out in the middle. So again, my thought was correct. It's a disc because there's no opening on this axis of rotation because the axis is one of the boundaries. So we're going just regular R and H, right? And the H is a dy. The radius comes from this axis of rotation back here. There's our radius. Understand, it's a changing, this is the point xy, right? So the distance from the y-axis over is the x value, isn't it? And if we want to get the radius, we're going to start out with the 5 and subtract out the x value. Alright, well, if y equals x over 5, then x equals y, 5 over y, right? So we could call this 5 minus 5 over y because we know we need it in y's. So we're ready to integrate pi. Remember, disk is just based on pi r squared h, right? For the volume. And the radius, 5 minus 5 over y squared dy. And the y values, well, I did kind of mention right here that at 1, 2, 3, 4, 5, x value of 5, the y value is 1. So that lowest y unit is 1, and it ends there at 2. So it's a pretty small little area. If we need to FOIL that out, not if, because we need to multiply those. 25 over y doubled would be 50 over y plus 25 over y squared, I believe. I'm going to do one more rewrite. 25, well, 50 over y I'm keeping because that's an ln, but make this 50, 25 y to the negative 2. Now, integrate 25y. Gosh, I wonder if we should have pulled out a 25. That would have been so much easier. Oh well. Minus 50 ln, absolute value of y. Add 1 to the power be negative 1. Divide by negative 1. Y to the negative 1, we'll just make it like that. Don't forget your pi outside. And then plug and chug. If we're going to do free response, just do it. Minus 25 over 2 minus 25 times 1. Natural log of 1 is 0. Minus 25 over 1. Distribute. So negative 25, positive 25 goes away. 50 minus 25 halves, 100 halves minus 25 halves, 75 halves minus 50 ln 2. I think that's as far as I can take it. Again, this could have been the free response. You could have just said 50 ln 1 right here and not had to remember that it is 0. All right. So I feel like we've done enough of, different, rotation volumes. The very last type of problem is this whole idea of cross sections. And I don't even remember this topic from when I was in college. It's kind of like I don't remember slope fields much from when I was in college. But cross-sectional volumes are almost easier. For some reason, kids make it harder. But if I just give you, two random equations, let's say the base of a solid is bounded by let's go y equals x squared and y equals 2x plus 1 minus 1, sorry. Okay. Well, we know what y equals x, okay. And then it'll give you an extra little, because it is called cross-sectional volumes. It'll say the base of a solid is bounded by these two graphs, and cross sections perpendicular to the x-axis are squares, the easiest one. Seen it many times on the AP exam, so don't feel like this is, oh, she's just making it too easy, because I've seen many times squares. But, so, as long as you can graph, and usually they're decently easy graphs, y equals x squared, I certainly hope you know how to graph that. 0, 0, 1, 1, negative 1, 1, parabola. 2x minus 1, start here, rise 2, run 1. Uh-oh. Sorry, people. Let's make it 3x plus 2. Sorry. 3x plus 2. There are only 4 problems in this whole book, so I can't take one of your problems to do, or you'd only have 3 to practice. So, 3x plus 2 has a y-intercept of 2. Rise 1, 2, 3. Run 1. Down 2, 3 over 1. This is the base of a solid. Now, I wanted it to be a, I'm sorry, people. I wanted it to be nice, even intersections, and these are not. So I'm going to force it into being a nice even. Let's try it. 3x minus 2. Rise 3, run 1. Oh, found a nice intersection point. Rise 3 more, run 1 more. So 2 would have been up here at 4, right? Oh, I think I found the intersection point right there. So this is linear. So those, I mean, that area is so teeny tiny. I'm just going to bring it right out here. And we're going to at least have a little bit closer look at it. The cross sections are perpendicular to the x-axis. So if I slice that a little slice perpendicular to the x-axis, the little height of the slice is a clear dx, right? And what I usually do is I will show, okay, well, they said that slice is a square, right? So I'm going to take this slice out and lay it on its side and draw out that little square. Or actually, I stretched it out a little bit more. And it turns into this little 3D prism, right? And that dx right here, that is a change in x value, is just right there. And you might remember from geometry, hopefully, that the volume of this prism is really just the area of the face times the thickness. And since it's a square, then that's just going to be side squared, right? This side times that side. Well, what we have to remember is how do we get that length from the 7-1 section? Well, we might say the top minus the bottom, right? The top y value minus the bottom y value. And the top y value came from the line, right? So this is a 3x minus 2 minus the x squared. That is the length from here to here, pretending I just stretched it and turned it over there, right? And since it's a square, this is the same, right? 3x minus 2 minus x squared. And so the area of that one little prism is the 3x minus 2 minus x squared, quantity squared, dx. But the whole idea of a definite integral is summing up all of these infinite little bitty things. Now, the interesting thing is, what does this figure even look like? And you're going to have to look on page 468 to get like some good 3D drawings of what these figures look like. They're just kind of weird. Like one of them, if this was equilateral triangles, it would look kind of like one of those, well, an axe head that comes into, a point, or one of those wedges you slide into to chop wood. But what's that called? Anyway, the easy part here, there's no pi, because there's no pi in the area of a square, right? It's just side squared times the thickness. We do need to know where the x values go from. And clearly it was from x equals 1 to x equals 2, right? Now, if you're not sure of those, if your drawing was weird, the way we can find those intersections is the same way we did, hopefully, in the 7-1 section, where you just set them equal to each other. You see my issue when I had a plus 2 originally? This was what I was trying to get to, so I could factor it nice and easy. So it definitely intersects at x equals 2 and x equals 1. So that's how we get those limits of integration. Hopefully, one like this would be on the calculator page, because that's not an easy thing to FOIL out, but it is just, Algebra 2, maybe even Algebra 1. I think I made my Algebra 1 kids. See, minus 6x minus 3x squared minus 6x plus 4 plus 2x squared minus 3x cubed plus 2x squared plus x to the fourth. So let's go descending order. X to the fourth minus 3x squared, x cubed, to 4 minus 3 is 1, plus 9 is 10x squared, negative 6x minus 6x is a negative 12x, plus 4. Hope I did that algebra correct. My math skills are leaving me. I'm sure yours are too. Add 1 to the power, divide by the new power, plus 10x cubed over 3, squared over 2 be 6x squared, plus 4x. And let's free response it, because nobody wants to do all that math, but 2 cubed over 5, 2 to the 5th, over 5, minus 3 times 2 to the 4th over 4, plus 10 times 2 cubed over 3, minus 6 times 2 squared, plus 4 times 2, minus, parenthesis, 1/5, minus 3/4, plus 10/3, plugging 1 into everything, minus 6 plus 4. Let's free response it and be happy with ourselves. So, the one I made up was not beautiful, but actually it was a good problem. We did have nice even intersection points. Obviously, if it's a calculator problem, you could just graph those two on the calculator and second trace intersect and get those, and you'd save those x values. In this case, if they were perpendicular to the x-axis, you would save the x values, store them in, and it would be a wonderful problem. So let's do another example of, let's say the base is an ellipse. Now, I hope you all have some form of recall or have been exposed to an ellipse, but if not, an ellipse is in this form. It looks kind of like a circle, only a circle would have x squared plus y squared equal like the r squared. So the radius would have been 1, or if it was 100, the radius would have been 10. All an ellipse does is, instead of making it a perfect circle, on the since the 16 is under the x, the square root of 16 is 4. 1, 2, 3, 4 to the right, 4 to the left, since it's the x. 5 squared is 25, so 1, 2, 3, 4, 5 up, 1, 2, 3, 4, 5 down. I kind of squished my y. Maybe I need to stretch them just a little bit more. Let's go 1, 2, 3, 4, 5. Let's just make them like that. 1, 2, 3, 4. Oh, just make them full units. Alright. Clearly, oops, it's like an oblong. It's not a perfect circle. It's not really an egg like I've drawn it, but it is called an ellipse. So, and we studied last year in pre-calc like all about the foci and all this junk. Just as long as you know how to graph the thing, you're good. So let's say the base of this figure is an ellipse, and let's go cross sections. let's go perpendicular to the y-axis. Or let's do the easy squares first. Same thing we did before. But since we were going perpendicular to the y-axis, I thought I would just... Now, if I'd drawn this correctly, it would have been perfectly symmetrical on the right and the left. I realize my drawing is quite imperfect. But since it's perpendicular to the y-axis, the little width of it is a dy. And that's a pretty doggone big slice, so I'll make it kind of big here. That I cut out here. And we have that little square prism dy. Now this is a little bit weird because we know the distance from the y-axis over is an x value, and because of symmetry this would also equal x, so I hope you would agree that that whole length would be 2x, and since it's a square it'd be the same thing over there. Now I'm going to kind of cheat on this one because I know as we're doing the volume of this, it's going to be the area of the face, or 4x squared, right, dy, and our y values go from -5 to +5, or let's use some symmetry and let's go 0 to 5 and double it. However, the reason I say I was cheating is because I knew that I can quite easily solve for an x squared up here. X squared over 16 equals 1 minus y squared over 25. Multiply by 16, and I got it, right? So 2 times 4, 8 out here, 0 to 5. X squared would just be, well, I guess I could say 16 times 1 minus y squared over 25 dy. And so really, see, 2 times 4 was 8. And then when I solved up here, I just had that 16 times the 1 minus y squared over 25. So I could actually just multiply. 6 times 8 is 48. 128. Integral 0 to 5 of 1 minus y squared over 25 is the same as 1 over 25 times y squared, right? And the integral of 1 dy is just y. It's going to be y cubed over 3. So that's going to be 1 over 75 y cubed. And then it's probably just as easy to not even pull out a calculator. 5 minus 5 cubed over 75 minus a bunch of zeros. 5 cubed is 125. 25 goes into that 5/3. 5 minus 5/3. That's 15/3 minus 5/3 would be 10/3. 5, 6, 7, 8. Not divisible by 3, so 1250 over 3 would be that exact volume. Grab my calculator just to check my work. Now, I could not check it from, oh, got 17 new messages. I haven't had my ringer on. Shoot. There it is. No, I cannot check from this version. That's mixing x's and y's. I can't do it. I can only check from this version. And now, when I plug it in, I can still do an x. 0 to 5, 16. I do that all the time. I thought I arrowed over. 16 times 1 minus x squared over 25. That already took care of the squaring, right? Okay. And dx. Math, enter, enter. Uh-oh, I put 1250. Five times 3 is 15, minus 5 is 10. Oh my gosh, I can't copy. I changed 128 to 125. How many of y'all caught that? Glad I checked it. So I did the easy one. Let's just do one last. These are kind of long videos. I'm sorry. Let's do the same one. Only let's go. So I don't have to draw it again. Let's say that the cross sections are not squares, but they're. Let's say they're rectangles with the height of 2. Well, rectangles with the height of 2 means that length is still 2x, right? Oh gosh. But the height is just a 2. And so really, we're just looking at 4x dy. Integral 0 to 5 and double it, right? Now, on this case, we would have to find, this would not be as easy to do because we'd have to take the square root of all that junk, okay? So, let's not do it. You get the idea. Just read carefully. It's a rectangle height 2. That's all you do. But what if it was a semicircle? So that big thing we pulled out is a semicircle, and it's still like a prism thing. So you're dealing with the area of the face times the thickness, which was still a dy. And what we need then that's a semicircle, right? So that's half pi r squared, isn't it? So now the r, if we kind of glance up here, the radius is just one of those x's, correct? So we're looking at 1/2 pi times x squared, and again times the thickness. Well, just like the square version, the x squared was pretty easy to solve for, right? 16 times 1 minus y squared over 25. So that took care of the x squared. We have a 1/2 pi outside. Anytime you do these over and over, you're going to find, if you use different figures, there's one problem in the homework, and it just says they're squares. They're equilateral triangles. They're, whatever. So just understand you're going to be using a lot of the same values. Go 0 to 5 again and double it. So we automatically get rid of that. Take the 16 on the outside. So because it was a semicircle, that pi did show up, right? 1 minus y to the 5th over 25. On it squared, the smurf, dy. 1 dy goes to y, minus y cubed over 3 times 25 is 75 again. And in fact, I believe we already know what these two subtracted without the coefficient, it was just 10/3. So I'm going to cheat and say that was 10/3 times our coefficient, 16 pi, would be 160 pi over 3. Hope you followed along. Sorry, this is some of my pre-calc work. Hopefully this gives you a good little base. There are lots and lots of AP style questions. As I post this, I might try to find another textbook that has even better problems, because again, this has 2 legitimate problems, number 71 and 72, for this cross-sectional volume. So I will I'll write up the assignment from our book here. Problem pages 4. I would stretch this out, guys, all week. This is your last assignment for this whole week, other than as you might be working on some of that AP review if you're taking that AP exam. 465 to 468, don't have a cal. 1 through 21 odd. 25, 29, 33. Now 37 and 39 have pictures of calculators, so do the setup only. Let's just do 41 and 43. And then I'm going to have you just skip all the way over to do the cross-sectional ones. 71 and 72. So it's not a huge amount, even though it looked like from the page numbers. But good luck. Again, text me, email me with any problems. I will try to post some of those answers so you can look. And as we move forward, I'm hoping to have a little better understanding of what I'm going to have to do for the dual kids versus the AP kids. Good luck.